Welcome in the video Elementary Particles Part 3. In the previous videos of this series, we reviewed 12 of the 18 known elementary particles. These are 6 leptons and 6 quarks. The remaining 6 elementary particles are Gauss bosons and Higgs boson. Bosons are sometimes called force particles because it is bosons that control the interaction of physical forces such as electromagnetic and gravity. The name boson comes from the surname of Indian physicist Satyendranath Bose, a brilliant physicist who worked with Albert Einstein to develop a method of analysis called Bose-Einstein statistics. According to particle physics, a boson is a type of particle that obey the rule of Bose-Einstein statistics. These bosons also have a quantum spin with integer value such as 0, 1, -1, 2, -2, etc. Let's talk about Gauss bosons. In the Standard Model, 3 out of the 4 fundamental forces have a force carrier particle, that is Gauss boson, but there is no force carrier particle has been found for gravity. Most physicists believe that leptons and quarks interact by producing and absorbing Gauss bosons. The 4 Gauss bosons are experimentally observed. Let us start by examining these one by one. The electromagnetic force is responsible for keeping a magnet stuck to a metal. It also keeps electrons bound in orbitals around the nucleus of an atom. So without electromagnetic force, matter could not exist. Photon is the electromagnetic force carrier boson and known as a particle of light. The photon itself is a massless, uncharged boson with spin 1. These are stable and are their own antiparticle. Second one, Gauss boson is gluon. Just as photons, gluons are the carrier or messenger of strong nuclear forces which form and hold proton and neutron together in nucleus of an atom. As we know, there are 2 up quarks and 1 down quark in a proton. Also, 2 down quarks and 1 up quark in neutron. These quarks are glued together by particles called gluon. A gluon has the ability to change the color of a quark in order to keep overall color change of the particle neutral, that is red plus blue plus green is equal to white. Like photons, gluons are massless, uncharged, spin 1 boson. Furthermore, gluon possesses color charge. They can interact with other gluon. Since gluon possess any one of 3 colors and any of 3 anticolors, actually there are 9 color combination of gluons. Antigluons are also gluons because reversing all colors result in another gluon. The weak nuclear forces is able to change one type of particle into another at short distance. It is responsible for phenomena such as radioactive decay in unstable atoms. The weak force is mediated by 3 different bosons, W positive, W negative and Z neutral. All 3 particles are spin 1 boson and have mass. Since W boson have electric charge +1 or -1, a weak force interaction can change not only the type of particle but also the charge +-1. For example, a down quark can decay into an up quark by emitting W negative or by absorbing W positive. Weak decays, which involve Z0 boson, do not change the charge of the particle. The W positive is the antiparticle of W negative and vice versa. The Z0 is its own antiparticle. In addition, there are other fundamental boson particles but without clear experimental information. According to the Standard Model, the Higgs boson is the particle that gave rise to all masses. On July 4, 2012, scientists at LHC announced that they had good reason to believe they had found evidence of the Higgs boson. Further research is going to get better information about the particle's exact properties. It is predicted as a boson due to its quantum spin value of 0. Second one is graviton. It is a theoretical particle which has not been found experimentally. As all other forces explained in terms of Gauss boson, it was very natural to attempt the use of same mechanism to explain gravity. Prediction of a quantum spin value of graviton is 2. Last one is bosonic superpartners. Under the theory of supersymmetry, every fermion would have a So for undetected bosonic counterpart, since there are 12 fundamental fermions, if supersymmetry is true, there are another 12 fundamental bosons that have not been detected yet due to their higher instability. They decayed into other forms. Thanks a lot. Watching again. In next video, we discuss about hadrons.